Let's take a look at some of the problems on the Math 1101 midterm review. So number 1, it says Megan weighed 5 pounds at birth and gained 18 ounces per month during her first year. We want to complete the table of values for Megan's weight, W in terms of her age, M in months. Okay, and so we're just going to fill in some of these values in the table. Okay, one thing that may help if we want to go ahead and write a formula. Okay, and so we could say W is equal to, initially she weighed 5 pounds, and then she's growing by 18 ounces per month. We want to ensure that this rate of change, the 18 ounces per month, is in the correct unit of measurement. So we want to actually have it in pounds per month instead, since the initial weight was given in pounds. And so we can convert to pounds by just dividing by 16, because there's 16 ounces in 1 pound. So 18 over 16 is 1.125. So altogether, we have W is equal to 5 plus 1.125 M as our formula. And then we can fill in these values in the table kind of quickly. Okay, so I've gone to my calculator in Y1. I've entered the function. And then if we look at the table under second graph, okay, we can see all of these values that we're trying to write down. So after 2 months, her weight would be 7.25 pounds. After 4 months, 9.5, etc. Okay, if we want to graph this equation, we really just need 2 points to graph a line. And since this is definitely linear, we could use the y-intercept, which is at 0, 5. And just one of these other points that we found. So when M is 4, W is 9.5. And then connect those points with a straight line. We can then use the formula to answer parts D and E. D can come from your table. And so you see after 9 months, Megan would weigh 15.125 pounds. And then when did Megan weigh 9 pounds? We can say that the weight is 9. So 9 equals 5 plus 1.125 M, and solve this equation for M. Okay, so subtract 5 from each side, and we get 4 is equal to 1.125 M, and then divide both sides by 1.125. So we end up with M equals 4 over 1.125, which is about 3.6 months. Okay, number 2, we're asked to graph the equation by finding the intercepts. Use the intercepts to find the slope of the line. Okay, so this equation happens to be in this modified form of general form of a line. So x over a plus y over b is equal to 1. Okay, and so we can rewrite this as x over 6 plus y over negative 12. Just move that minus to the denominator, is equal to 1. And then the x-intercept is at x equals 6, so 6, 0, and the y-intercept is at y equals negative 12, or 0, negative 12. Okay, well, this makes it very easy to plot the graph. And so I would just on the x-axis go over to 6, put a dot. On the y-axis, go down to -12, put a dot, and connect those 2 points with a straight line. The other thing that we're asked to do is find the slope of the line. And so the slope of the line can be found if we know 2 points as listed as ordered pairs using the slope formula, y2 minus y1 over x2 minus x1. And so in this case, it's -12 minus 0 over 0 minus 6, or -12 over -6, which is +2. In problems 3 and 4, we're trying to decide whether the given relation represents a function. And so first, if we're given a table of values, you're going to look for in the inputs or the independent variable whether one repeats, because that means it's paired with more than one value of the dependent variable. So in this case, we see that -2 is not only paired with a -4, it's paired with a 3. So this relation is not a function. If you're given a graph, the easiest way is to use the vertical line test. And so if you draw a vertical line anywhere on the graph of a relation, it should only intersect the graph one time in order for it to be a function. And we see this vertical line intersects the given graph in multiple places. So this is also not a function. Okay, let's skip to number 7. The water level in Lake Huron alters unpredictably over time. The graph below gives the average water level L of T in meters in the year T over a 20-year period. So we're asked to find L of 1997. Okay, so we look on the horizontal axis to find 1997, and then locate the point on the graph and determine what that water level is. And so referring back to the vertical axis, we see that's 177. And that is in meters. In which year did Lake Huron reach its highest level according to the graph? Okay, so we're looking for a maximum, and the highest point on the graph is this one. Okay, so we look at when that happened, and that is 1986. And the level, we refer back to the vertical axis, and so 177.25 meters. And then lastly, part C. During which year or years was the water level below 176.25 meters? So we locate 176.25 on the vertical axis, sketch a horizontal line, and find the intersection of the graph or intersections of the graph with that horizontal line. Okay, so we're going to say somewhere in 1999, right before 2000, it dropped below that water level, 176.25, and then it stayed that way for the rest of our graph. So we're going to say this is 2004. So from 1999 to 2004. Now, in 1999, it was equal to 176.25 meters. So we're going to put parentheses at 1999. 2004, the water level was definitely below 176.25. So we're going to include that year in our answer. Okay, let's take a look at number 9. It says auto registration fees in Connie's home state depend on the value of the automobile. The table below shows the registration fee, R, for a car whose value is V, both given in dollars. So we want to determine whether the data are linear. Okay, well, we have a couple of options. We want to look for a constant rate of change. So if we find the change in R over change in V, for each pair of these consecutive points, we just want to show that ratio is the same every time. So I think we can do this kind of quickly. You're just going to do 235 minus 135, so 100 over 10,000 minus 5,000, or 100 over 5,000. And that simplifies to 1 over 50. And then do it again and again. Okay, so 100 again, the change in R's, over 5,000, the change in V's. Okay, so we're going to say yes, the data are linear since the rate of change is constant. You're also going to have to write an equation for this linear function. And so another option, and this works for both parts A and B, is to just use your calculator to find the linear model. So under Stat and then Edit, you're going to just enter this data in your lists. Okay, then select the Stat button again, Calculate, and number 4, Linear Regression, and hit Enter till it calculates. Okay, so the first thing that would answer part A is to determine whether the data are linear. Hopefully your calculator is set up correctly to show R squared and R at the bottom of your screen, and R is the linear correlation coefficient. So if R is 1 or -1, the data are completely linear. But at the same time, we found the slope and the y-intercept of this line, so we can write the equation in part B. So R of V is equal to 0.02 V plus 35. And lastly, it says give the slope of the line and explain its meaning in context. Okay, so we found the slope. M was 0.02. Okay, it's often nice to make this a fraction if it's not 1, and then write what ratio this really represents. So typically change in Y over change in X. In this case, it's change in R over change in V. So you could say something like this: as the value of the car increases by $1, the registration fee increases by 2 cents. Okay, another thing that you could do, maybe to make it a little bit more appropriate for the context of the problem, is to transform this fraction. So maybe multiply the numerator and denominator by 100. So find an equivalent fraction. So 2 over 100. Okay, so you could say as the value of the automobile increases by $100, the registration fee increases by $2. Okay, in number 10, we're asked to write an equation for the given line. And so if you want to write it in slope-intercept form, which is often how we write our equations, it's y equals mx plus b, or y equals b plus mx. Okay, either one. But to find the y-intercept, just look at the y-axis and locate where the graph crosses. So b is -5. And then what if we want to find the slope of this line? So try to find another point with clear coordinates, so probably integer coordinates, and then you can count the rise and the run. Okay, so how to get from one point to the next. So I would count up 1, 2, 3 spaces and right 1, 2 spaces, and the slope is therefore 3/2. Okay, so altogether our equation is y equals 3/2 x plus -5 or -5. Okay, let's take a look at number 12. It says, according to the U.S. Census, the population of Lexington, Kentucky was 261,000 in 2000 and 296,000 in 2010. So we want to write a linear function for the population of Lexington as the function of t, the number of years after 2000. So what that tells me is t equals 0 is the year 2000. Okay, and then we can refer back to that starting year to write some ordered pairs. Okay, so in 2000, the population was 261,000. And in 2010, which is 10 years later, the population was 296,000. Okay, so now I have 2 points of the form t comma p. You can then write the equation by hand by just finding the slope between the 2 points and recognizing that this p of 261 is the y-intercept. That wouldn't be too hard and it wouldn't take a whole lot of time. The second option is to run linear regression, and in L1 you would type your t, so you would type 0 and 10. In L2 you would type your p's, or 261 and 296. Okay, so let's just do this by hand. M equals 296 minus 261 over 10 minus 0. And that's 35 over 10, or 3.5 is the slope. Okay, so our function, p of t, is going to be 3.5t plus 261. We could then use that formula to answer part B, which says, use your model to predict the population of Lexington in 2008. Okay, so remember, t equals 0 is the year 2000, so t equals 8 would be the year 2008. So in our population function, we're going to find p of 8. So 3.5 times 8 plus 261 is 289,000. Okay, in number 13, we're given a line that has a slope of 2/3. We want to find the vertical change associated with the horizontal change of delta x, which is -15. Okay, so just remember that the slope of a line is the same as calculating the ratio change in y over change in x. Okay, in this case, we're given a slope of 2/3. We do not know a delta y, but we are given a delta x is -15. So if we solve this equation, one option is to just cross multiply because it's a proportion. And we get 3 times delta y is equal to -30. And then divide both sides by 3. So that gives me delta y is equal to -10. Okay, we'll skip ahead a little bit to number 16. Determine whether 6, -1 is a solution to the system. Okay, so 6 is an x and -1 is a y. And so we're just going to substitute those values into each of these given equations, and they're each equations of lines. Okay, so -2 times 6 minus 4 times -1. And we want to see if this is equal to -8. Okay, so we're going to do the calculation. -2 times 6 is -12, and that becomes a plus 4. So that is equal to -8. Okay, so this point definitely satisfies the first equation, but we need to check both. So -3 times 6 minus 3 times -1, and we want to see if that's equal to -14. So we get -3 times 6 is -18, and then plus 3. Okay, well that's -15, which is not -14. So we're going to say 6, -1 is not a solution to the system. Okay, well, we also have some word problems involving systems of equations. So number 17, we see that adult tickets for a play cost $10 and children's tickets cost $7. Altogether, there were 36 people who attended the play, and the theater collected $300 from ticket sales. So we want to know how many children attended the play. Okay, so we don't know how many adults and we don't know how many children's tickets were sold. Okay, and because we don't know either of those, we need to set up two equations. The first equation is pretty straightforward. You just take the number of each of them, add them together, and you get the total number of people who attended, which was 36. The second equation is going to deal with the revenue that was brought in. So if each adult ticket costs $10 and they sell X of them, then 10X is how much money they will collect from selling adult tickets. Okay, using the same type of reasoning, if children's tickets cost $7 and they sell Y of them, then 7Y is the amount of revenue they'll collect from those sales. And then is equal to the total amount of revenue collected was $300. Now that we have this system, we have to solve it. And there are some algebraic techniques to solve this system. Another way is to graph both of these lines and find the intersection of them on our calculator. So I think that's what I'm going to do. First, isolate y in each equation. So in the first one, we get y equals 36 minus x. And the second one, you'll have to do a couple of steps, but I'll just write the final answer. Y is equal to 300 minus 10x divided by 7. Okay, and now in y1 and y2, enter each of these lines. Okay, so then I'm going to just try to find a good window. I'll start with Zoom Standard, Zoom 6. And even though nothing appears, if I hit Zoom 0, both lines should appear. But what I really want to see is where these lines intersect. So now maybe I'm going to try Zoom Out, which is Zoom 3. And just move your cursor to the location you want to zoom out around, which to me is in the bottom right-hand corner, and then hit Enter. Okay, so we see the intersection. Use the intersect feature, which is under second trace, number 5, and then hit enter 3 times. Okay, so x is 16 and y is 20. So out of those two, we're trying to find how many children attended the play, which we said was y. So our answer is 20. If we take a look at number 19, it says Earl borrowed $5,500 from his uncle for 2 years with interest compounded annually. At the end of the 2 years, he owed his uncle $6,474.74. What was the interest rate on the loan? Okay, so we have a compound interest formula, and it looks like this. A is equal to P times 1 plus R to the N, or to the T, where N or T is just how many years that the account that the person has been saving. Okay, so we start with a principal, which is the initial deposit, $5,500, times 1 plus R to the second, because it's for 2 years, and A is the later balance. Okay, we can then solve this equation one of 2 ways. We can use algebra and use the extraction of roots method, or a graphical solution and use the intersect feature. Okay, so let's go ahead and go back to the calculator and see if we can use this method. So in Y1, enter one of the sides of the equation. And in Y2, enter the other. Okay, so since this is a new graph, I'm going to start over with trying to adjust my window. So zoom 6 for zoom standard, and then zoom 0 for zoom fit. Okay, we see at the bottom of the screen it looks like 2 intersections, but we want a positive intersection because, or positive R value, because the interest rate should be positive. So find the intersection that's on the right. Okay, and that occurs when x is about 0.085. Okay, so that tells us R is about 8.5%. Okay, for number 22, we want to use the table to determine if the function is increasing or decreasing, and then to determine the concavity of the function. Okay, so the first thing, if x is going up, which it is, we can look at the y values to determine if the function is increasing or decreasing. And we see from one y to the next that it gets smaller and smaller. So the function is decreasing. To determine the concavity, you can analyze the rate of change of the function. It's really how it's changing. So change in y over change in x, you can take each pair of consecutive points and calculate that ratio and see what's happening as x gets bigger. Okay, so we'll do a couple of them and then I'll show you one other option. So 0.8 minus 1 over 1 minus 0 is is negative 0.2. Okay, and then we can do another one, 0.64 minus 0.8 over 2 minus 1 is negative 0.16. So it appears, if I compare these numbers, the second one is the bigger of the two. And so it appears that the rate of change is going to be increasing. I do want to test out these others as well. And if that happens, if the rate of change is increasing, the graph is concave up. But another way to kind of tell is to look at the graph of the scatter plot. Okay, so I would just edit my lists, enter this new data. I'm going to turn my scatter plot on, and so the fastest way to do that is under y equals. Okay, just go up to the top where plot 1 is located and hit enter. And you should see that it's highlighted. And then just hit zoom 9 for zoom stat. Okay, so the graph kind of looks linear, but there's a little curve to it. If I had to decide how this is curved, if it's curved up or curved down, it's definitely decreasing, but it looks more like it would be in a U-shape pattern than an upside down U-shape. So that's another way to tell that this is concave up. Okay, and number 24, it says determine the basic function used to model the given scenario. Okay, so volume, its volume of a hot air balloon is a function of its radius. Volume, you can kind of think about it, it's in cubic units. And as long as it's depending on one length, like in this case, it's just a radius that the volume depends on, that radius is going to be cubed. It's kind of like a cube. So volume equals 4/3 pi r cubed. If you're just talking about the volume of a cube, it's side cubed. Take one of the sides and multiply it by itself 3 times. So it's at volume equals side cubed. And if that's the case, then you know that this is a cubic function. Okay, but part B is a little bit harder because it says the length of a rectangle as a function of its width. If the area is 24 square feet, okay, so you could think about, here's my length, here's my width, and the area is 24. Like that is definitely consistent every time, or it's constant. So if the width is 3, the length would then be 8. Okay, if the width is, say, 4, the length is 6. So if the width gets bigger, the length gets smaller, or vice versa. Okay, so we kind of have an idea now that we're talking about a decreasing function. If you happen to know the area formula for a rectangle, that may help us decide which type of decreasing function this is. So if A is equal to the length times the width, and you're given the area is 24, and we want to write the length as a function of the width, which means solve for L. So we get L equals 24 divided by W. Okay, we only have one basic function that looks like this, where we have a fraction and a variable in the denominator, and that's the reciprocal function. So that is what we're going to say best fits this scenario. And then one other, the sales tax on a purchase as a function of its price. Okay, sales tax, if it's 8%, it's a rate, and we could write it as 0.08, that no matter what, as my purchase price increases, say by $1, the sales tax I'm going to pay increases by this amount, by say 8 cents on the dollar. And so you could also write a formula, maybe sales tax, I'll say T, is equal to 0.08 times the sale price P. And we can see that this is linear, and both P and T are raised to the first power. The rate of change of this function is constant. It's that 0.08, which is the slope of the line. And so we'll say linear, a linear function. Let's take a look at one more. It says Bob goes skydiving on his birthday. So the function h of t approximates Bob's altitude t seconds into the trip. So we want to know, what is Bob's altitude after 100 seconds? Okay, so 100 seconds. Because this is a piecewise function, we really have 4 formulas that we can use at different times, but we only use one at a time. And so we want to look at where 100 falls, and that is when the time is between 0 and 400 seconds. So that means we use the first formula to answer this part of the question. So h of 100 is 25 times 100, or 2,500. And I think this should be in feet. Okay, and then after 400 or 450 seconds, 450 falls in the next domain, which is this kind of restriction that we have on our times, or t's. And so we're going to use this second formula to answer this part of the question. So h of 450 is equal to 10,000. Now, this is a constant, this 10,000, which means that for so many seconds, he stayed at the same height, which is probably when the airplane reached that altitude, and then he's going to jump, and the height will change after that last number of seconds, after 500 seconds.